Yeah, thank you for having me. Thank you to the organizers. I'm aware that this is technically a reunion conference, and I was not here last year. I, I went back and forth to maybe as a joke I should look up, see if there were any pictures from the conference and Photoshop myself in the background giving thumbs up to everybody, but maybe not. Yeah, but thanks to my wonderful advisor, Jordan Ellenberg, in the back there. He kind of vouched and asked if I could be invited because I worked on this project this summer with an undergraduate student, actually, Sunny. This was through the kind of Baruch College, New York City discrete math RU. And frankly, this was a ton of fun. And I don't know, I mean, I think that the results are really quite interesting. So I'm excited to present it. Yeah, so hi, everyone. My name is Eric. Thank you for having me. Yeah, so today I want to talk, oh, I said all this. Okay, great. The basic outline is as follows. There's a conjecture of Erdos about independence numbers of trees always forming a unimodal sequence. The purpose of this project to start was to get evidence for or otherwise break this conjecture using AI methods. So the structure of this talk will first quickly run through some background. Before detailing the entire 2-month process of computer experimentation, my intention is for this to feel more like a historical narrative about the successes and failures of the process rather than something that's really pristine and it's here are all the great results. It's okay, here is me trying something and failing and then picking myself up and trying again until, wow, it worked. All right, so let's get into background. So for a given graph G, by an independent set, we mean a set of vertices which are pairwise non-adjacent. The independent sequence is the integral sequence A1 ... up to A alpha, where AI is the number of independent sets of size I, and alpha is called the independence number of the graph. Okay, so I'm sure all of this is known, but I just want to make sure that there's, we've kind of standardized our terminologies. So it is a famous fact that this sequence is unimodal and in fact real-rooted. This is a much, much stronger condition, but it is unimodal if G is a claw-free graph. This was the stronger real-rooted version of this was proven by Chudnovsky and Seymour. Now, it was proven by Alavi, Malda, Schwenk, and Erdos that this unimodality is extremely untrue for general graphs. And what do I mean by extremely untrue? Yeah. So think about it this way. So, okay, I'm going to give you a map from graphs to permutations, and I'm going to do that by, given your graph, write the independent sequence, and then permute it so that it's increasing. Okay, that's the permutation you get on the other side. So what those authors prove is that that map that I just described is surjective. So every possible permutation is achieved by some graph. Okay, so not only is the independent sequence, generally speaking, not always unimodal, you can essentially get any behavior that you'd like if you look across all graphs. Okay, but now in that same paper, they conjectured that the independent sequence of trees should be unimodal. Now observe one thing, which is that, okay, what is known? Claw-free graphs, independent sequence, really well behaved. This is a conjecture that says that for trees, essentially something similar should be true. Now, trees and claw-free are on the opposite end of some spectrum, right? The whole point of a tree is to have tons of claws. So these would be two extremes, and you're unimodal on either end, and then in the middle, pretty much chaos happens. But at least at the two ends, you should have unimodality. All right, so this conjecture was later generalized by Galvin and others to state that the independent sequence of trees should be log concave. What I mean by that is that if you take any index squared, this should be no smaller than the product of AI plus 1 and AI minus 1. This is the log concavity condition. So-called because if you take the logarithm of both sides of this inequality, it becomes just concavity. All right, cool. Yeah, so this is log concavity. Now, log concavity implies unimodality, essentially because like if you had something which looked like this, then at that point where you switch from down to up, you would break log concavity. So log concavity implies unimodality. Yeah, so this was a stronger version. And now this stronger version of the conjecture stood for decades. And in fact, it was verified computationally for all trees with at most 25 vertices. So for all trees with at most 25 vertices, it was proven that the independent sequence is log concave. Okay. And then it stood that way for a long time. And in 2023, Kadrawi and Levit proved that there are exactly 2 trees on 26 vertices that fail to be log concave. And that for both of these trees, the breakage happens at the index I is equal to 13.
So why did they stop at 25?
Great question. I think, so this work, the 2023 work, came out of a paper which was basically like, hey, here's this like clever dynamic programming approach to computing independence sequences of trees, with the idea being basically like, okay, if you take any graph, but a tree especially, like if I want to know the independence polynomial, well, it's essentially like look at the root of the tree. It's either in the independent set or it's not in the independent set. And so this gives you kind of like a recursive way. And for trees, so anyway, so they're like, hey, with this kind of dynamic programming approach, like this algorithm is actually really efficient. It runs an O of n time to compute the, so like, let's try 26 vertices. Oops, we found we found a counterexample like immediately. Why the original authors stopped at 25, I guess I'm not 100% sure. It seems like at the time that was essentially the best that they could do. Whatever.
It's super unfortunate. I know from which point of view, but
Yeah, I mean it's one of these humors. You know the old expression, right, which is like you know, humans plan and God laughs. It's like an alternative version of this is like anybody makes a conjecture in combinatorics and God laughs, right? It's like it's so frequent where we have these conjectures and we have so much evidence, and then it turns out if you just went a little bit further than what was previously done, it just kind of breaks.
I just looked up in the OAS. This is one of the very first sequences, number 55. How many trees there are and that many vertices, and there's already like 100 million trees with 25 vertices.
Yes.
And more than twice as many on 26. So
Yes.
back then it wasn't so trivial to check all of them.
Absolutely. Yeah. So this is going to be a recurring theme in this talk, which is that the tree sequence grows quite fast. The number of trees on n vertices, that is. Okay, so here are the 2 counterexamples on 26 vertices. They look suspiciously similar. Okay. So here are the 2. Okay. So keep an eye on this, right? So keep these pictures in mind because I'm going to kind of keep referencing them. Like the way that these counterexamples look, it's like root has some number of children, and each one of those children has the same number of children, and the children of the children are paths rather than single vertices. Does that make sense? Where it's like, oh, instead of thinking of this being the child, think this entire kind of edge here is the child. Okay, so in fact, it was shown that each of these 2 fall into 2 natural families of trees. Now, in all cases, the breakage happens at the index, which is exactly half the number of vertices, and either 1 or 2 below the top index alpha. So these are the 2 families that I'm talking about. So it looks like this. The top family is called the 3KK family for obvious reasons. So again, root connected to a child with 3 edge children, another child with K edge children, and another child with K edge children. 3KK. And this one was called 3 star KK plus 1. Okay, so again, families of counterexamples. Now, following this, in February of this year, Galvin produced a family of examples with a parameter t. So for t greater than or equal to 4 has a single breakage, one single breakage in the independent sequence, which happens approximately at half the number of vertices. Now, as the number of vertices goes to infinity, this break happens further and further from the top index. So in other words, the purpose of Galvin's paper was to be like, for any k, can we find breakage which happens at index alpha minus k? And this family kind of illustrates that you can. Yeah.
I mean, not important, I can't get my head away from it. But on the previous slide, why did you have k plus 1 rather than k minus 1?
So here,
Right.
so why is this k
K
plus 1?
rather than k minus 1.
So
Okay, just.
So if you notice, this one has 4, this one has 3.
No, it's just talking about notation.
Oh,
K plus 1K or K minus 1K.
so are you saying why isn't this like 3-star k minus 1k?
Yeah, just we had the same number.
Yeah, so they add up to the same.
Yeah.
Oh, I see.
Somehow.
I see. Okay, so in my defense, this is their notation, not mine.
Okay. I can move on.
Apologies. Okay, so this is Galvin's counterexample. Look, once again, very similar to the previous, right? So in this case, you have a root which has t children, and each one of those t children has t edges as children. All right. Incidentally, when we started this RU, at the time I was familiar with the original kind of counterexamples, but I actually had not seen this paper of Galvin, which at this point was only a couple months old. So on the first day I meet with Sunny and I described the project, and she's like, and she actually was like, wait, didn't Galvin put out a paper on this topic? And for like 5 minutes, I was like, please God, don't tell me that Galvin solved the problem. And now I prepared for this whole month's research. Anyways, it turned out well. All right. So as of the beginnings of my project with Sunny, these were all of the known counterexamples to the log concavity conjecture. So let me kind of make some important notes here. So in all cases, these are counterexamples to log concavity, but not unimodality. Unimodality is still conjectured. It's still, for right now, seemingly it's okay. Okay. Number 2, in all cases, the breakage happens at exactly one index. We still do not have a single example where log concavity breaks and it breaks in 2 places. Don't have it. Number 3.
Have an example with actual concavity breaks?
What do you mean?
Well, if I remember right from the abstract, first of all, it was conjecture that's actually concave,
Yeah.
and then there's a strong condition of log concavity.
Yeah.
So just because log concavity breaks, it might still be concave.
Oh, I see.
That's what you're looking for, isn't it?
Yeah. So ultimately what we're going to be doing here is just like, producing kind of lots of these kind of counterexamples. Yeah.
But of the
Yeah.
log case.
In the log case, correct.
Didn't you study just a concavity case?
So we didn't, let's see, we didn't specifically look at concavity. I think but as far as I can tell in all the examples we looked at, I think that should still hold. So I do not know whether, concavity.
Be the big news, right? If Erdos is.
Right. Yeah, that's right. Okay. Now, I just also want to note, as I've said a few times, all of these counterexamples have a very similar vibe. It's like a root connected to some number of vertices, each of which have like an equal or near equal number of children. And all of these children are paths of some kind, edges or longer. Okay. So now that's the background and the combinatorics. So now let's switch gears to our chosen AI architecture. So for this project, we hope to use Machine Assistant to produce more and more examples of trees which fail log concavity. Again, the idea being like maybe if we're super lucky, one of these failed log concavity examples will also happen to break Erdős' conjecture. But in any case, at the very least, it gives us a sense of like why this log concavity is failing. So we ultimately used PatternBoost of Charton, Ellenberg, Wagner, and Williamson. So the main idea of this architecture, which has been brought up already, is as follows. So you start with some combinatorial problem that you're trying to solve. You then come up with a scoring function for which higher scores means better solutions. Start with some number, about, for us, 50,000 of random samples. Run each one of these samples through some optimization algorithm. Now, importantly, kind of the bitter lesson, as it were, here. This algorithm does not need to be sophisticated, right? We're not looking for some ultra optimized anything. It can be just a greedy algorithm. But the point is that the optimization algorithm just needs to make your scores slightly better each time you run it. So now, once you've optimized your 50,000 starting samples, you send those samples to be training data for a transformer, which you train, and then you ask it to produce some number of samples. So for us, it'll be like 100,000. And now each of these samples is sent back to the optimization algorithm and run through the optimization algorithm, and then you keep the top 50,000 to send back to the transformer, and so on and so forth. This is the PatternBoost idea. And here's a nice diagram kind of illustrating the cycle here. Okay, so in other words, to start here, we have to determine three things. Yes?
When you, every iteration, do you retrain from scratch or do you try to reuse it?
So you reuse, so start here, 50,000, which you've optimized in some way. This is sent to the transformers. Transformer is trained on this and produces 100,000, this shouldn't be 50, 100,000 samples along with the 50,000 original.
So what I meant that you retrain the transformer from scratch, or do you reuse the parameters, the weights of your previous iteration?
Oh, I believe the weights are reused in PatternBoost, right?
I have no idea.
Oh, I'm sorry, I'm talking to Jordan.
Okay.
So in ultimately, because the training loss is less and less generation over generation. So I believe that it's reused, isn't it?
But I think we're giving it new prompts, so to speak. Like it's being, I mean, it's being passed like a bunch. I mean, I guess it's make more is being passed like a bunch of vectors, and it's saying make more like these. So it's
right.
It's trained the way make more is already trained.
Yeah. Okay, so to start, we have to determine three things. Number one, what is the scoring function? Number two, what is the most efficient way to encode our trees to be understood by the transformer? And number three, what is the optimization algorithm? Okay, these are the three things we'll need. So the first of these is the easiest, right? So we define the score of any input graph just by the log concavity inequality, but just kind of as a difference, right? For any fixed chosen index I, you can define this, right? Which is essentially checking the log concavity-ness of the sequence at index I, okay? Now, observe that a tree fails log concavity at I if and only if this number is positive. That's the idea. Okay. All right. Now, because of the existing history of counterexamples, we initially focused our attention specifically to look at number of vertices over 2. Okay. So I'm only paying attention to that particular index. For any input tree, I look at half the number of vertices, and then I try to check what the log concavity-ness is at that index. As I said, the existing counterexamples all break at n over 2 on the nose or somewhat close to n over 2. So this is where I'm going to check at first. Okay, so next we need to decide how to encode our trees. So an obvious way to do this is by flattening the adjacency matrix into a string. This is terrible because at the very least, you're ignoring a lot of symmetry. For instance, you don't need the entries of that matrix below the diagonal. But even accounting for this diagonal issue, we can actually encode our trees in a much more space-efficient fashion using proof for coding. Okay, so a proof for code is a sequence on the alphabet 1 to n, whose length is n minus 2, right? And it's a well-known fact, due to proofer, I suppose, that these sequences are in very natural bijection with labeled trees on n vertices. Okay. By a labeled tree, I mean a tree with n vertices where each vertex is labeled with 1 to n. Okay. Now, note that there are at least 2 drawbacks to this particular representation. The first is that we don't really want to work with labeled trees, right? What I care about is the independent sequence, and the labels on the vertices here don't add anything. And in fact, when you think about it, so remember what was said before, which is that like on 25 vertices, there's like 100 million trees, right? 25 to the 23rd power is considerably bigger than 100 million. So I am, by using this particular representation, I'm in some sense introducing a colossal amount of noise, right? So again, this is like first thoughts, like let's just try this kind of thing. You know, so these are potential drawbacks that we were aware of. And again, by miracle, it ends up working even despite this. The second drawback here is that the proofer code, like when you just think about the proofer code written out, that you cannot just from eyesight, as far as I can tell, extract the independence numbers from the proofer code, right? It's not like, oh, if you take the proofer code, do some combinatorial ninjutsu, boom, there's the independence number, right? It's like, it's not obvious how one goes from proofer code to independence number, aside from proofer code to adjacency matrix to independence number, right? So that extra step might be hiding things from the transformer. It turns out it doesn't, again, interestingly. All right, so our final and most technical challenge will now be to decide on an optimization algorithm. So ours proceeds as follows. So given an input tree, choose a non-edge to add. I'll talk more about how you make this choice, but choose a non-edge to add to the tree. Okay, call this edge E. Now, by adding an edge to a tree, you always create a unique cycle by doing that, right? So what I'm going to do is I'm going to walk along that unique cycle, and I'm going to say, try to remove every single edge one at a time, and check the score of each one of those trees that results. And then just choose the one that has the biggest score, basically. So replace T with the tree obtained from the prior step with the largest score bigger than the original score of T. So when this operation that I just described, I'm just going to call it an edge swap. So basically I had an edge, I introduced a new edge, I deleted the original edge, and that's a new tree with a bigger score. Now the above is repeated until some prescribed number of swaps happens. So usually this number is 10, but I'll talk more about this later. In principle, you could just do this once, right? Do it once, your score has gotten bigger by definition, and that is what we're looking for. This optimization, the point is to make the score bigger. Okay, all right, so got it. So the first goal of this project, after installing all the many mountains of packages, was to use these techniques to rediscover the original n is equal to 26 vertex counterexamples shown before, right? Like this is the proof of concept. Yeah, in the back.
Can you go back?
Yes.
Why it's not obvious to me that it's not optimal to delete the edge E that you just added. So why is it necessarily?
Right, great question. So let's say you add this non-edge, you go around, and the biggest thing you can find is the original tree. In other words, you've deleted. Okay, so then that is not considered a swap. That's considered a fail. And then you just try the next non-edge.
So this could happen. So this is not monotonically increasing the score.
No. I mean, sorry. Yes, I guess in theory, you could try this for every single non-edge and just never find anything that makes it go up. And then, yes, then that is in principle possible.
That's a failure mode that doesn't happen.
Yes. So, yeah, correct. Yeah. Okay. Now, note that even pulling this off would be a meaningful step because, as I said, there are 9 times 10 to the 33 labeled trees with 26 vertices, right? 9 times 10 to the 33. This is a astronomically colossal number. And there are two kind of families of counterexamples within those. So this is really needle in a haystack. Yeah.
going to try to understand something here, but
Yeah.
so there are that many, a huge number of labeled trees.
Correct.
So you want trees, you don't care about the label. Correct. But your generative model, presumably you train it from data or something like that, and you have a particular way of representing each tree. You have an algorithm that goes from trees to labeled sequences. Yes. And this algorithm will favor certain type of representation, right? So it's not actually your generative model is not trained on this entire set of labeled trees.
Right.
It's trained on a tiny subset of that. So your generative model is trying to generate only trees, which only labeled trees which have been generated in a particular way.
Sure. So like for instance, like the way we start is literally just being like, okay, create like. Literally, we start by saying create a random sequence on the alphabet 1 to n of length n-2 and do that 50,000 times. So we start there. And then each one of those goes through optimization and then is sent to the transformer. That's how this whole process starts.
Oh, okay. Sorry, I get it. Nice.
Right. Also at this stage in the process, we did not have access to GPUs, so we had to run everything on our local machines. By consequence, at this stage of the process, we only ever asked the transformer to produce 50,000 samples rather than 100,000. We only performed a single swap, one single edge swap during optimization, and only ran experiments for 5 generations. In other words, transformer, local, we did that 5 times. Also, at this stage, we were at the non-edge during optimization was added literally at random. So like choose a non-edge at random, and that's how optimization was being done. So our kind of early tries looked like this. So it does seem, to be clear, like, again, counterexample means you're past 0. Now, it's not totally clear because of resolution here, but this is like just to the left of 0. This spike here, this is at negative 256. Or around there. Does it, just out of curiosity, does anybody want to guess where that wall, what tree that wall is? The path. As you
Is it fast to calculate the score?
yeah, actually. So oh, this is yes. So as I said, we were running all of this on our local machines, and you know, I don't have like some crazy Alienware thing. I mean, doing this took like just maybe a couple hours, up to 5 generations with all those other parameters. Yeah, so it was quite fast. Okay, it's a bit hard to tell, but the outputs cannot quite get over the 0. In fact, even if you ran the experiments for more epochs, what frequently happened was that the machine outputs began just converging on just spitting out the path graph over and over and over again. So like, as I said, just to the right of, or just to the left, sorry, of 0 is this spike where it seems like things are like gathering, and that turns out to be the path graph. And indeed, like running this for more epochs was not making things better. It was just making the transformer better at printing the path. Okay, so now we have to tinker. You know, the joke, which is not my joke, but it's a joke that I told Sunny all the time when we were doing this, is like sometimes science is more of an art than a science. So, okay. We decided to make 2 changes to what we were doing. Firstly, in our optimization algorithm, we changed the code so that non-edges were chosen to have the highest possible degrees of its 2 endpoints. So remember, originally I was adding a non-edge randomly, but then we made the conscious decision to like look at all the non-edges, sort them by the degrees of their 2 endpoints, and add the one that had the biggest degrees of the 2 endpoints. The reason for this is, at least, again, like I figured that it would encourage branching in the trees that were being created. And because everything was converging on paths, I was like, well, to break that, we want to encourage branching. The second thing we did, we began filtering out any trees for which the number of leaves was too large relative to the total number of vertices. So one concern that I had was that, wait, if I encourage branching, is this just going to converge on the star rather than the path? because that would be a disaster too. Huh? Oh, sorry. So I also want to encourage like not too many leaves relative to the number of vertices. And in some sense, when I say that, what that means is that if you have a lot of vertices but not many leaves, that means you have a lot of vertices of degree 2. So after making both of these changes, we successfully recovered both of the 26 vertex counterexamples. In the experiments, we found that in the experiments that found the two, it usually did so within the second or third generation. So it did it like pretty much immediately. All right, emboldened by this, we pushed our local machines to their limits by looking at trees up to 32 vertices. Interestingly, at this time, though this would not continue, but at this time, we found counterexamples at all even vertex sizes, but not the odd ones. Okay. Now, to be clear, when I say this, like we ultimately get on the supercomputer and we found counterexamples everywhere, right? But on the local machines with these parameters that I described, like the odd vertex sizes somehow were harder for the machine to find the counterexamples at first. So we found all these counterexamples, all of which did not fall directly into the previous known families, but many of which had the same vibes as those families. That whole idea of like this connected to children, which are connected to paths, right? Now, importantly, around 32 vertices, examples started exhibiting behaviors unlike those previously known counterexamples. For instance, this one, or these two, sorry, they're two. So here are two counterexamples on 32 vertices that are starting to look a little bit different than the kind of patterns we were seeing before. A lot more kind of branching where it wasn't there before. Okay, so it was around this time, which was literally the last day of the RU, that we got access to the GPUs. And started bringing things up to scale. So at this time, we increased the number of samples requested to 100,000. And at first, we said, okay, optimization step, do swaps until you literally cannot do swaps anymore. Remember, we said there's a failure state wherein like you try to add every single non-edge and not a single one of them produces a better score, right? So I'm just going to keep doing this like swap until you drop, right? Moreover, those two like crutches that we added, the like not too many leaves and always add a big degree edge, we removed those. Okay, those were genuinely crutches because our machines were not powerful, and at small vertex sizes, like it seems like they were necessary because those examples were so relatively rare. So on the swap until you drop change. So this latter change, while it seemed correct on the surface, actually had two major drawbacks. So firstly, it took an astronomical amount of time to run. Because like if I'm looking at every possible non-edge, and every time I add one, I look at the entire cycle that's created, and I'm just computing independence polynomials like crazy, it took way too much time. Moreover, when we ran this for a few epochs, one example, we got something that looked like this. Does anybody want to guess the graph that's to the left of 0 there?
It's the path again.
It's the path. For some reason, no matter how much I try to avoid it, like PatternBoost falls in love with the path.
Isn't that because you got rid of that? You said you got rid of that crutch that made it attached.
Correct. I got rid of the crutch, but for some reason, there's some kind of local minima or maxima here where like something draws me to
But if
the
you
path.
left that crutch in, would it not do that? Because I thought that was trying to prevent it from converging onto the path.
Correct. So like with both of the two crutches in, because like the vertex or the leaf crutch is not preventing the path, right? But with both of the two crutches in, yes, it like basically avoided the path because it had to. But if you remove them, you always find this behavior where amongst the kind of negative side of things, it finds the path very frequently. Yeah.
Maybe I probably missed it. It
Yeah.
just occurred to me that maybe there's something here because paths are cooperating. And like there's some like extreme tree value there. But
Yeah, no, I mean, absolutely, it could be something like that. What it feels like is that like in terms of our score, which remember is looking at the penultimate, or rather n/2 index and checking the log concavity there, it feels like the path is the least negative, but still negative score that you can get. It's like you have the path, and then once you get past the path, you're in the promised land. Now, just to be clear, this here, even though it looks like one single example, it's actually 4 examples that it found about 10,000 times. So now the issue is that PatternBoost is only trying to make the scores as big as possible, right? So coming back here, PatternBoost is literally only trying to make the score as big as possible. Like that's what it was designed to do. But I'm not trying to make the score as big as possible. I am trying to find anything with a positive score. And so what's happening is if you optimize too aggressively, PatternBoost is just like, oh, here's a positive number, but it's not positive enough, and it throws it out and it just jumps to the one which is as positive as it can possibly make it. So in other words, the goals here between what I want and what PatternBoost wants are not totally aligned. So we spent the next few days running many experiments. Essentially, PatternBoost, myself and Sunny went to therapy together, and we aligned our goals. It turns out that 10 total edge swaps was a sweet spot, where if you do 10 edge swaps, it is optimizing the situation enough to be viable, but at the same time, it's not optimizing it so aggressively that PatternBoost tends to make things so big and positive, it ignores the small positive numbers. Okay, yeah. Okay, so at this point, once we got onto the supercomputing clusters, we have found now hundreds of thousands of counterexamples across vertex sizes 26 to 101. So one of our greatest successes was 60 vertices. In this case, the machine ultimately found over 40,000 unique counterexamples. Okay.
You also checked Erdos conjecture on all of these?
Yes.
Yeah.
And all of them are still good with Erdos. So now I give you this. This is the 60 vertex example. And you're like, what's going on here? First of all, does anybody want to guess what that large thing to the left of 0 is? Okay, it's the path again, I know. Now, you're like, what's going on here? Well, the idea is that, in fact, there's literally 45,000 little dots here because it found 40,000 things once. Right? Now, on the scale here, they're not going to appear. But in fact, across this entire x-axis here, it found 40,000 different counterexamples. So the vast majority of these counterexamples do not look anything like the original batch. In fact, as we increase the number of vertices, counterexamples begin to look more and more like literally random trees that have just been subdivided. So for instance, here is a counterexample to log concavity on 60 vertices. That pattern of just like vertex with children and each of those children or have paths as children, that's like completely gone at this point.
Any relationship between a graph and its sub-tree and subtrees?
In terms of like this.
Conjecture.
So let's see, subtrees.
I mean, I want to like.
Yeah. So I think in general, no, or not like in any obvious way. Yeah. But yeah, so this is an example, just one counterexample that we found on 60 vertices. Now, obviously, like this quote unquote log concavity score was a means to an end, right? Like it's just some gadget I'm trying to make positive for my own ends, right? But you could ask the question of like, what do those scores actually look like? So the smallest positive score that we found was 9. Okay, so there exists a tree for which the log concavity score here is 9. So just barely failing log concavity. And you also get trees like with like log concavity scores positive 10 to the 9th, 10 to the 10th, etc. Okay, so
Wait, can I ask a question?
yes.
are we still just checking the log concavity score at n/2?
Yeah, I'm about to get to that. Yeah, but yes, good point. So right now we are only checking the log concavity score at n/2. Okay, so I want to point out certain failures of this approach. So to start, our methods have not been able to find a single example of breakage away from half the number of vertices on the nose. Now, as I said, Galvin's example breaks near, quote unquote, near n/2, but not necessarily at n/2 on the nose. Okay, so we know for a fact there should exist counterexamples where breakage happens away from n/2. Okay, but now I have been doing this for days and weeks and weeks and weeks and weeks. And no matter what I do, no matter how I tinker, no matter what I do with the parameters, PatternBoost cannot find any counterexample with breakage away from n/2. It can't do it. Not only can it not do it, it doesn't even seem like it's trying, right? Where it's like, it starts with the 50,000, let's say I'm like, hey, PatternBoost, try to find breakage at n 5n/12 or something like this, or n/2 - 1 even, right? And PatternBoost looks at the random samples and basically hands me back things that look exactly the same. And then they're optimized a little bit. And then PatternBoost is like, I'm going to just hand you back what you give me. So the scores just do not improve. And it's the darndest thing. Like anywhere I look away from n/2, PatternBoost just basically gives up immediately. It can't really do anything. Whereas with the n/2 case, where we've had all this success, PatternBoost is finding these mountains of counterexamples after just a few generations of kind of optimization. So there is something important about that n/2, which I have no idea what it is. Yeah, so in fact, when we look at any position that's not n/2, the machine really never makes any headway at all. Scores remain basically unchanged. And yeah, unfortunately, we haven't been able to make that work. Now, with this kind of in mind, if you kind of put all the jigsaw pieces together and you squint, this actually suggests to me that the original Erdos conjecture is going to be true. So why do I say this? Okay, so let me kind of put all the jigsaw pieces together here. So first of all, as I said, like if there were a tree whose sequence was not unimodal, where the kind of curve happens there, where you're going down, but then you curve back up, the log concavity needs to break there, okay? So number one. Number two, it is known that the final third of the tree independent sequence is always decreasing. The entire final third of the tree independent sequence must be decreasing. Number three, it is known that if you take a random graph, or random tree, asymptotically, almost surely, the first 49.5% of the sequence is increasing. Okay. And number four is that the independence number of a randomly generated tree is about 56% of n. Okay. So putting all those things together, what it suggests is that if you fail unimodality, you would have to find breakage essentially somewhere between n/4, which is n/2/2, and like essentially 1/3 and 1/4. And the fact that we can't find anything other than at this particular spot, which is not in the Goldilocks zone, tells me actually that unimodality is actually, in my mind, actually more likely to be true. Sorry if that was incomprehensible, but I could talk more about it later. Okay. Moreover, by consequence, we are unable to find any example where breakage happens more than once. So this is another thing that, given the hundreds of thousands of counterexamples we now have, all of them, log concavity breaks exactly once. We don't know if it can break more than once. Right. Another unexpected problem. So picture this. So I'm bored and I'm like, you know what? I'm just going to push this n to 101. Okay. 101 vertices. That's a lot of vertices. I'm going to try this. it gets about 2 generations in, and I'm like, this is taking a long time, as you might expect. So let me just make sure that there's nothing silly going on. Let me look at the outputs of the transformer. And I look at the output of the transformer, and it's like, oh, hey, this is a counterexample. This has a positive score. So let me take this tree, and let me just look at it. And I pass it to the code, and I'm like, this tree has negative 200,000 independent sets of size 25. And then I'm like, first, I'm like, I don't know. I invoke my high school self who was like, what if there was negative weights? And then I'm like, no. No, I'm an adult. And then I'm like, oh, right. Integer overflow is a thing. Okay. Once you get up to a certain number, you can't actually be working with integers anymore. So you have to use what Julia calls big int, which is just integers, but they're allowed to get a lot bigger. Now, it turns out that if you use big int, if you just go through my code and replace every int type with a big int type, well, not every, but like the ones that are relevant, it slows things down to the point that just nothing becomes, it's like shocking how much doing this slows everything down. Okay. But now I just want to point out the final kind of, at least to me at the time, miracle. That counterexample to log concavity, which had negative 200,000 independent sets of 25, when I fixed this and I used big integers, it actually was still a counterexample. Okay. And here it is, if you're interested. It's hard to parse. So,
And did it actually have that score, or was it just congruent modulo some high power of thing?
no. So like what was happening, right? So if you think like the independent sequence, it's like assuming unimodality, is going to be biggest in the middle, and then by the end it's smaller. So it's like the n over 2 index here was using kind of genuine integers, because those numbers were not quite as big as the middle. Okay, but now what this essentially says is that the machine genuinely does not care what's happening with the rest of the independent sequence, because like the rest of the independent sequence, there was complete nonsense happening in the middle. But it's like, hey, I'm really somehow only looking at these big independent sets. I am completely ignoring the small independent sets. And you might say like, oh, but your score function only uses the big independent sets. And I'm like, yes, but remember, how does one compute the independence polynomial of a tree? It's done inductively, right? So to produce the big independent sets, you have to ask, well, what are the smaller independent sets that you can build, right? So I thought that somehow implicitly the machine would care about the middle of the independent sequence having any sense to it at all. But then it turned out that no, it didn't. It really somehow did not care at all about these middling independence numbers and was only looking at the big ones, which by chance were not big enough to be integer overflowed. Very strange. Okay. Yeah, and I think that's all I have to say. So thank you.